As we have acknowledged before, turbines generally they are very rugged and reliable machines. So in this section, we are going to be looking at the steam turbine. So we'll be looking at the various components in the steam turbine and how the steam turbine converts the kinetic energy that is contained in steam into rotating mechanical energy. So that is what we'll be looking at in this section. Then subsequently, we will be looking at some common faults or problems associated with the operations of the steam turbine and what we can do to remedy all of these situations. So the steam turbine, as you can see on your screen, they basically can be used to drive various plant equipment, rotating equipment, as we will see later in the course of this program. Okay, so we are going to look at how we need to understand the steam turbine, okay, as in the various components that is contained in the steam turbine and what those components they do, their function within the steam turbine and how they interact with one another to help produce the overall function of the steam turbine. So we are going to look at the main components of the steam turbine, okay? The various components that are in the steam turbine, the main one basically. Then subsequently we will look at those auxiliary components that are needed for the proper operations of the steam turbine. Then we are going to look at the operating cycle, okay, of the steam turbine, starting from the steam intake into the turbine and then to the exhaust of the used steam, okay, from the steam turbine. So in the course of looking at these operating cycles, we are going to simultaneously look at how the steam turbine works, okay? So we are going to summarize this operating cycle with how the steam turbine actually functions. Remember, the understanding of these two steps, okay, the operating cycle and how it works. In fact, these three first steps, they are very important for the proper operations and maintenance of the steam turbine, such that when anything is happening within the turbine, you're able to discern which particular component of the steam turbine is responsible or will likely be responsible for such fault condition. So we are going to look at all of that. Then we are also going to see the various types of steam turbines that we have in the course of this program. And then we will see the applications of steam turbine. Okay, what can we use this steam turbine to do in our various facilities, which I know you're already familiar with. So we are going to look at them briefly, then the advantages of steam turbines. Okay, so let us look at the major components of the steam turbine. So what are the major components of the steam turbine? Okay, so like we said in our previous section, the steam turbine is actually a very simple rotating mechanical equipment, very simple machine. Okay, so it is basically made up of the stationary part, which is the stator, and the rotor. Those are the two major components of the steam turbine. While on the rotor and on the stator, okay, we have other components that makes the steam turbine to function properly. So we are going to see all of this. So the first we are going to be looking at is the stationary part, which is the casing, as you can see on the screen. So this is the casing, okay, which is the part covering this particular part that is rotating. Are we getting it? So the casing is the stationary part of the steam turbine. Remember, we said we need the steam turbine is made up of these two major components. This one, which is the rotating part, and the stationary part, the stator and the rotor. Okay, so this is the casing. As we'll see later, the casing also have other components on them. Then we have the rotor, which is this particular shaft, okay, that is rotating, that is responsible for converting, that is the rotor together with other components on the rotor, is responsible for converting that kinetic energy in the steam, as we'll see later, into rotating mechanical energy. Okay, so this is the rotor, and the naming is by virtue of the fact that during normal operations it always rotates. Okay, so that's the rotor. So like we said earlier, there are other components on both the stator and the rotor, as we saw in the case of this earlier diagram. Okay, so this stator, we have blades on them. Okay, then on the rotor too, we have blades on them too. So on the stator, the first set of blade before you go into the turbine proper is called the nozzle. It's called the nozzle. Okay, so the function of the nozzle is actually to throttle the steam to increase the velocity and thus the kinetic energy of the steam that is entering into the turbine. So once it is throttled, this is the nozzle now, okay, which is always the first stage of the steam turbine. So if this is the nozzle now, you see that as it's going through, we'll see all of those later. Okay, it will throttle, just assume it is this. So as the steam is going through, here is wider than the rear, okay, as the steam is coming out. So that constriction helps to throttle the steam, okay, thereby increasing its pressure, its velocity. Remember, as it is coming out of this spacing, it is now re-exposed to a very wide, that is a larger volume in the turbine. So once it is exposed to that larger volume, what happens to the pressure? The pressure will drop. So that fast moving steam will impinge. Remember, you have the nozzle have increased the velocity, will impinge on the rotor blade, okay, and that will cause the rotor blade to turn, as we'll see later. Okay, so that's the function of the nozzle. It is usually the that's the function of the nozzle. Then we have the blades, as we have seen earlier. Then we also have the bearing. Remember, the rotor needs to have that free movement, okay, around the casing, has to rotate freely. So one of the components that assists the rotor to rotate that freely is the bearing. Are we getting it? It is the bearing. So the bearing does two things basically. It supports the weight. We have one at the front and another at the rear. Okay, so it does two things basically: supports the weight and then to ease the rotation of the rotor around the uh, around the casing, okay, the turbine casing. So that's the bearing. Okay, we have one here and another here. So in larger turbine or a larger rotor, there is always need to have another bearing within the, that is in the middle of the rotor. Okay, so we have another joiner where bearing will have to support the rotor at that particular point. Okay, so basically put it at the back of your mind to aid free rotation and to support the weight of the rotor. So that's basically the function of the bearing. Then another major component of the steam turbine that is very key to the smooth operations of the steam turbine is the shaft seal. The seal, okay, or the sealing system. Remember, steam is injected into the turbine. Are we getting it? And remember, since we have this rotor shaft going through the casing, there must be an opening around that shaft to allow free rotation of the shaft. Okay, and also too, since we need to transfer that rotating mechanical energy to an external equipment, okay, that needs that rotating mechanical energy, it therefore means that the shaft must protrude, must come out from the casing, okay, or from within the turbine. So that point where the shaft protrudes out of the turbine, you see that there must be some clearance around the bearing. Okay, so and since we are having steam of higher pressure, steam with pressure that is higher than that of the surrounding atmosphere, the tendency of that steam being of higher pressure forcing itself through those clearances or openings around the rotor shaft, okay, is there. So two things will definitely happen. If the pressure, okay, if the steam, if the steam is escaping through that space or through that clearance, what will happen? You see that the efficiency of the system will be reduced. And again, since we need bearing at this end and we have steam coming out, definitely that steam will affect the bearing, okay, will cause the bearing to operate at a pressure that is higher than at a temperature that is higher than that for which it is designed, and thus causing the early failure of that bearing. So we need a system that will help to prevent the escape of that steam to help us maintain the efficiency of the turbine. So that is basically the function of the shaft seal, to help contain the steam, okay, within the turbine casing, to help maintain the pressure within the turbine casing, not allowing the steam to escape. Okay, so we will look at that too later in more detail. So this is the shaft seal. So we have labyrinth seals. We'll see how the labyrinth seal actually functions. The labyrinth seal, or whatever sealing system that is used, what it does is that it prevents the steam from escaping to the uh, to the outside. Let me put it like that. Okay. Then in condensing turbine, you see that where the area where the the steam is exhausted, usually lower pressure is created around that area. Okay, as we'll see later. So if lower pressure is created here, pressure that is lower than the atmospheric pressure, so that the tendency of air entering into the system through that shaft opening or clearance, okay, the clearance between the rotor now, the rotor shaft and the casing itself will be there. Okay, so once there is that escape of air into the turbine, that will definitely affect the efficiency of the steam turbine, because it will affect the condensation or affect the vacuum of this area. We will see all of those later as we go along. So we also have another major component, which is the governor. Okay, so the governor actually controls the amount of steam that is injected into the steam turbine. Why is it doing this? It is doing this to control the speed of the steam turbine. So the governor basically is a component in the turbine or steam turbine that helps to control the speed. of the steam turbine. So you know that the rotation of this rotor, okay, is dependent on the rate at which the steam is actually impinging on the blades, okay, on the rotor. Are you getting it? So if you can control that rate, that will help to control the speed. So that is exactly what the governor does, regulates or control, okay, the rate at which that steam is administered into the turbine, and thus controlling the speed of the machine. So we will look at it in more details later, but these are the various components of the steam turbine. We have the casing, we have the rotor, we have the nozzle, okay, which are the blades on the stationary part of the turbine. Then we also have the rotor blades. That's the blade that actually converts the kinetic energy in the steam into rotating mechanical energy. We have the bearing that helps to allow, apart from supporting the weight of the rotor in the turbine, helps to ease the rotation of the shaft on its axis. Okay. Then we also have the seal that helps to prevent the escape of steam from within the turbine, thus helping to maintain the efficiency of the turbine. And also we have the governor that helps to regulate the speed or control the speed of the steam turbine by controlling the rate at which steam is administered into the steam turbine on the blade of the steam turbine. Okay. So we have the steam intake system, that is where the steam is administered into the steam turbine, and the exhaust system, that is the discharge, okay, of the steam haven't done its work. So the steam with low energy, okay, going out of the turbine goes out through the exhaust system. Okay. So, and this is, here we have the exhaust system because the steam is administered, okay, this is a low pressure turbine. The steam is administered into the turbine. This is where it comes in, okay, and then it's pressed both ways, okay. So the steam that comes this way is exhausted through, this is the exhaust, and here we have another exhaust, okay. We'll get all of this clearer later as we go along, okay. So that's about the intake and the exhaust system, okay. So we've talked about the bearing. See, this is a larger rotor. As you can see on a larger turbine, you see that we have journers, okay, within the turbine, okay. So in this, as we see, is a multi-stage turbine. We will come to see all of this later. So these journers, you see how these journers, they are supported by bearings apart from the end bearings. Are we getting it? So the function of the bearing is also to ease the rotation of this rotor. This is the rotor now around the casing. This is the casing, the stationary part of the steam turbine, okay, and also to support the weight of the rotor itself. So that's the two basic functions. So here is a single two-stage steam turbine, okay. So here we have the sealing system, okay, the seal to help prevent the steam that is administered into the turbine from escaping through the shaft clearance. Then here we have the bearing that supports the weight of the turbine, the rotor, and allows it to rotate freely within the turbine, okay. So this is the bearing, this is the seal, and here we have the rotor, okay. So the rotor, we have two blades, two sets of blades. So it's a two-stage. Are we getting it? It's two-stage steam turbine. Okay. So this is the bearing as we have discussed. This is one that is coupled on the ground. Okay, so we have the bearing. So this is the internal surface of the bearing that actually does the work. So we always have oil, thin film of oil around this journal bearing, okay, that actually separates the shaft. We'll see that later. Separate the shaft from the bearing, okay, to decrease the wear and tear of the bearing, okay. So the shaft C, as we have seen before, this is the shaft C. So its work is to prevent the escape of steam, okay. So this is another picture of the turbine, the three stage. So here in the middle here we have the blade of the stationary blade here and here, okay. And the work of that stationary blade is to direct the fast moving steam onto the blade of the rotor for the rotor to turn. So this is the seal. As you can see, it's a labyrinth seal. So as the steam escapes through each of these section of the labyrinth seal, you see that the pressure of the steam will be reduced, and eventually it will cancel out, because as the steam is escaping in each of this library section, okay, turbulence is created as it escapes. So that turbulence, okay, helps to prevent, acts as that is, produces back pressure, okay, that tends to act against the one that is coming from inside the turbine. That is the one that is coming from inside the turbine that is trying to escape out, okay, from inside the turbine. So it will eventually cancel out or stop the steam from leaking out, because the pressure will have dropped as it's going out, okay. So that's the labyrinth seal of this three-stage steam turbine. So this is the labyrinth seal. What I was trying to discuss earlier. Imagine that the steam is, this is the part that is facing the internal part of the steam turbine. That is here, that is facing the internal part, okay. So as the steam is coming out, okay, instead of as it's trying to escape, assume that it escaped through this. So that turbulence is created, okay, that tends to want to act against the one that is coming. That invariably will reduce the pressure, apart from the fact that the this the hurdle created by this labyrinth, okay, has actually helped to reduce the pressure to some extent. So as that is happening, as you are going along, you see that the pressure will eventually drop to zero, okay. And then at the outer end of the labyrinth, there won't be any steam coming out until such a time when the labyrinth, okay, the seal is already wearing out. Remember, it's a mechanical seal, okay. And as this is turning, it can be eating the surface. Are we getting it, of this labyrinth? Because it will wear preferentially to the shaft itself, the labyrinth on the shaft itself, okay. So remember these ones too. That's something I've actually forgot to highlight. Okay, we have this kind of teeth here too, okay. So which means that it's a kind of interlocks in some of these labyrinths, okay. So that further help to create that impediment or resistance to the flow of steam out of the turbine. Okay, so in this is the governor of the steam turbine, Okay, then you see that the steam, this is the intake of the steam. This is connected to your steam line that helps to inject steam into the steam turbine. So this is the stop valve. Okay, so when you look at this stop valve, you see that it has a lever. Okay, that is you can hang on this trip, that is trip mechanism. Okay, so before starting the turbine, as we'll see later during normal startup, you lift this up. Okay, so as you are lifting this up, what happens? This valve will open up. Okay, so as you are opening the valve that is feeding the turbine, you see that since this is opening, okay, that will now administer the steam into the steam chest of the turbine. Are we getting it? So as it's going, this is the governor. Okay, we'll see the simple centrifugal governor later for us to have an idea of how the governor actually functions. So this governor actually controls the amount of steam that is administered into the steam turbine itself. So within the steam turbine, we have the stationary blade, as we have seen earlier. Okay, as we saw earlier, it has the stationary blade and the rotating blade. So the rotating blade actually converts that kinetic energy. Okay, the stationary blade is to throttle, its function is to throttle, increase the velocity before it impinges on the rotating blade. So the rotating blade is what is responsible for converting that kinetic energy that is contained in that steam into rotating mechanical energy. So that steam haven't done its work because the rotating blade on the rotor have extracted the energy from the steam. So that less energy steam, okay, haven't done its work, need to be exhausted. So it will now be sent through the exhaust, okay, to wherever, either to your condensate line or to your LP steam line, that is low pressure steam line. Okay, so as the case may be, or straight to your, okay, condensate line straight to your deaerator, as we will also see later, okay, in your steam system. So this is the these are the major components of the steam turbine, as we have explained earlier. So this is the the trip mechanism, the governor itself, okay, and then as you can see, you see this latch. This is the stop valve, which is this particular one that we saw, okay, that is here. This particular stop valve, okay, this the main steam stop valve, and that is what is here. So once it is lifted, okay, by lifting this up, this latch up, okay, you see that this will open up. So once it open up, the valve disc will lift, okay, and then that will allow steam, okay, through the intake, steam intake, to be administered into the turbine. Are we getting it? So now, if you look at the turbine, it goes through the governor, and the governor itself has a mechanism that is tied to the shaft itself. Okay, so that helps to look at the speed. Okay, helps the governor to look at the speed to regulate the amount of steam that is administered into the turbine. So the higher the speed, the lesser the amount of steam that will be administered, or that will be allowed by the governor. So as the speed is reducing, the governor will see it. That will make it to increase the amount of steam that is administered into the steam turbine. Okay, so if the speed is also increasing. Okay, the reverse case will always happen. So if you look at this mechanism here, this is the trip mechanism. Remember, you have set this here, and this is tied to the turbine shaft. Okay, so if the shaft speed is increasing, are you getting it? So if it increases beyond where the set limit, what will happen? The centrifugal force will help to push this trip pin out. Okay, so that trip pin will now push on this lever, and that will shift this latch back and free this lever. Okay, and then release the stop valve, which is this stop valve now. This is the stop valve. To release the stop valve, this is the latch. Okay, the trip pin will push on this. Are you getting it? As it pushes on this lever, where the latch will push backward and free this lever, and that will cause the valve to do what? To drop. When the valve drops, okay, it will close the steam. Okay, that is the valve. This disc will drop to shut the valve. That will now stop the inflow of steam, and that will help to shut down the turbine. So this is the emergency stop arrangement, okay, of the steam turbine, in addition to the governor that helps to control. So if the speed goes beyond what could be controlled, before it will result to catastrophic failure, this trip mechanism will be activated by this trip pin, okay, and short steam to the steam turbine. So put this at the back of your mind, so that when we are discussing the operations later, you know the reasons why you need to take certain actions during normal operations of the steam turbine. So to discuss the governor simply, for us to see how it helps to regulate the speed of the steam turbine, we want to look at this centrifugal governor. Okay, so if you look at it, this is the main shaft, the main shaft from the turbine itself, which means this is part of the shaft, that is part of the rotor. Are you getting it? And that protrudes out. So we have a jar system at the end within the governor. Okay, so you see that it is tied to this particular balance weight. Okay, so what happens is that as the speed of the turbine is increasing, since this jar is tied to this jar, of course the rate of rotation, the rotation of this will also do what? Will also go up. So as that is happening, what will happen to the centrifugal force on this balance weight? It will also increase. And as the centrifugal force is increasing, you see that the balance weight will tend to be opening up. Are you getting it? That is, we'll see it later demonstrated. You see, it will be right. This one will be going up, this one will be going up as the speed is increasing. So what will then happen? You see that since it is tied to this particular shaft now, okay, that is responsible for actuating or lifting the valve, that is the stem now. Let me call it the valve stem now. It's attached to the valve stem that is responsible for lifting the disc. Okay, you will see that as this is happening, the speed is increasing. What will happen? You see that the disc will push down, and that will tend to be reducing the space or the clearance, the space between the valve disc itself and its seat, thereby reducing the amount of steam that is administered into the steam turbine. Are we getting it? So conversely too, as the speed is reducing, you see that this balance weight will be dropping. Both of them will be dropping. As they are dropping, this will be lifted up, thus lifting the disc, okay, increasing the space between the disc now and the seat, which is this disc now and the seat. Therefore, that will mean that more steam will be administered into the turbine. So you see that the amount of steam that is administered into the turbine is actually determined by the speed, okay, of the rotor of the turbine. So with this kind of arrangement, you now be able to control the speed of the turbine. So we have other types of governor, but this is just to highlight how it functions so that we have an idea of what is actually happening within the turbine itself. So this is what we've been discussing. So if you look at this dead weight, you see as the speed is increasing, what happens? You see that the dead weight will be opening up. Okay, so as it is opening up, you see that this butterfly valve, okay, the disc of the butterfly valve will be closing. So as it is closing, that reduces the amount of steam that is administered into the steam turbine. And once the amount of steam is reduced, that will reduce the speed, okay, and that will reduce the speed here too. That will cause the dropping, as it is dropping now, of those balance weights. Are we getting it? So once that happens too, you see that the disc will open up completely. And once the disc is open up completely, more steam will be administered. Okay, so that is the basic idea of the governor. Whether you are looking at whatever kind of governor, electronic or whatever, okay, it looks at the speed of the engine, okay, to control the amount of steam that is administered into the engine. It's just like what we also discussed in the gas turbine. Okay, look at the speed of the engine to control the amount of fuel that is administered into the combustor, okay, of the combustion chamber of the gas turbine. So that is basically how it works. And finally, we are going to be looking at the intake. We've discussed this before: steam intake and the exhaust system. Okay, that is the point at which steam is administered into the turbine. Okay, goes into the turbine, does its work, does its thing, and then it comes out through the exhaust, having done the work, okay, that you need it to do. So that is the exhaust system. So this is what we are talking about. This is the intake, okay. This is the emergency stop valve. This is the intake. Then comes into the turbine, does its work, and then this is the exhaust system, okay. Then it is sent either to your lower pressure line or to your condensate line, as the case may be, okay, your LP steam, low pressure steam line. Are we getting it? Okay, so let us put all that we have been discussing together. So look at your screen now. We want us to focus. This is the intake, okay, and this we have the governing system, okay. Then this is the steam chest, administer steam into the turbine. This is the first stage, okay. So all here constitute the intake system, then goes through the turbine itself and then exhausted. Are we getting it? So we want to see that flow of the steam through the steam turbine. So we want to take note as it happens. So you see the steam coming into the steam chest, okay. The valve opens up, it is administered into the turbine itself, and then cause the rotation. Remember the first stage nozzle, cause the rotation of the turbine rotor. Are we getting it? So that is what will actually happen in the steam turbine. Okay, then it is exhausted. The steam that you have used the energy from will now be exhausted. Okay, so the exhaust system could be tied to condensate line or low pressure steam line, as we said earlier. So next now we want to look at the operating cycle, though we have discussed actually the operating cycle, okay, from the intake to the exhaust. Are we getting it? But let us just look at it briefly again. So remember, we need steam, and usually the steam is generated at the boiler house, okay, which is the beginning or the starting point of your steam system. So in the boiler, as you can see on your screen, on all of these boilers, treated water is converted into steam. So this treated water is heated up, okay, and then it is converted into steam. So that steam is what will now be sent through this your HP steam line to your steam turbine. Okay, so that is the first part of the operational cycle of your steam turbine. That is the steam generation. So in the steam generation section, what happens is that the chemical energy that is contained in fuel is burnt and converted to heat energy. Okay, so that heat energy within the boiler itself will be absorbed by the water. Okay, so the water will now convert that heat energy into kinetic energy in the fast moving steam. So that kinetic energy, okay, is what we are actually interested, that is contained in the fast moving steam. That's what we are actually interested in. Okay, so that's fast moving, that high kinetic energy steam will now be admitted, as we have been explaining since, will now be admitted into the steam turbine through the stop valve, the steam chest, the governor of the steam turbine. Okay, so it will now be admitted into the steam turbine. So once it is admitted, it goes through that first stage stationary steam turbine, which is the expansion nozzle, as we explained earlier. That helps to throttle it, increase the velocity further, which will further increase its kinetic energy. So that high speed, high kinetic energy steam will now impinge on the rotor blades, okay, or the blades on the rotor. So that rotor blade will now convert that kinetic energy into rotating mechanical energy that will be available on this shaft for us to do whatever work that we need to do in our plant or in our industry floor. Okay. Then within the turbine, we will explain this later. We have the impulse blade and the reaction blade. Impulse in the sense that the force of the steam impinging on the blade is what will now cause it to rotate. Okay, so we have that, and then we have the reaction blade too. Okay, remember that action and reaction, they are equal and opposite. So the action of the steam exiting the rotating blade can cause an equal and opposite reaction force on the blade that will also help to turn the blade further. Okay, so what you are seeing on your screen now, these are stationary blade on the stator of the steam turbine. So these stationary blades, as we have acknowledged earlier, they usually act as the nozzles, okay, that helps to throttle. Okay, so this larger part is usually on the exhaust side of the steam turbine. Are we getting it? So we will explain that later. Then this steam after being administered into the turbine itself, the kinetic energy will now be converted into rotating mechanical energy by the rotor. So that's the second stage, the next stage in the operational cycle. So this is the rotor. Okay, so if you look at this rotor carefully, you see that the earlier stages of the blades, the rotor blades, they are smaller compared to the side that is close to that is the later stages of the blade. So the question is, why are they designed like this? Remember that as the steam is leaving all of this earlier stage, they are becoming weaker and weaker because these earlier stages extracts the kinetic energy from them. Okay, and as it is expanding also, expectedly the energy will reduce. Steam, as the energy is reducing, it expands also. Okay, so these larger blades, they are meant to actually assist us to, as much as possible, extract whatever that is left, okay, the most, okay, that it can extract from that weak steam. Are we getting it? Or lower energy steam before it is exhausted. So the larger surface area is to help to extract more energy from that weak steam. So this is what we have been discussing. So this is the nozzle, and as it throttles the steam impinges on the blade of the rotor. Okay, the blade on the rotor, and that causes it to turn. Are we getting it? So in summary, as we have seen earlier, this is the operating cycle of the steam turbine. So what you have here is a multi-stage steam turbine. Okay, so we have, this is the equipment to be driven, which basically is an alternator of that is a power generation unit. So this is the HP section. Then we have the intermediate pressure section. Okay, then we have the low pressure or LP section of the steam turbine before it is exhausted. Okay, through the we have the condensate system also. We will see all of this as we go along. So this is an open up steam turbine. We have the stator, this is the rotor, and this is the blade on the rotor, or these are the blades on the rotor. So here between these two rotor blades, we have the stator blade. These are the stationary blades, so they are always between. Okay, between, you have the stationary blade. Then this is the line bridge seal that we discussed the other time. Okay, so let's try to get a closer view. Okay, so this is it. You see, this is the stationary blade and this is the rotating blade. So this is the line bridge. Okay, so we have another one on the cover of the casing. Okay, so still on the operational cycle, we've talked also on the exhaust, which is the part that goes out. This is the intake and this is the exhaust. Okay, from the steam turbine, and that is what you are seeing here: intake, exhaust, as we have discussed before. Okay, so apart from what we have discussed now, in larger turbines we have what is called the condensers, and such turbines, they are regarded as the condensing turbines. Are we getting it? As the low pressure steam, okay, on those multi-stage turbine, as you can see here, after going through the LP turbine, you see that the pressure will be so low, and can actually result to condensation, okay, that will affect the turbine. And again, remember that the flow would have reduced because the energy has reduced, okay. So to help increase the efficiency of the turbine, you see that in the exhaust system, vacuum will be created. Are we getting it? So that vacuum will help to pull those low pressure or low energy steam, okay, pull them into a condenser, which is basically a heat exchanger, as we'll see later. So that condenser will help cool the steam, those that are the low energy steam, and condense it to water, okay, which is the condensate or condensate, okay. So this is an example of what we have been discussing. So you see that this part that is exposed to this part, okay, you see the low pressure steam as is dividing towards both sides comes out from here and comes out from here. So all of them are joined together in this condensate, that is the exhaust line. So the low pressure is set up here, okay. So this part of the steam turbine is what is connected to this part of the steam of the condenser. Are we getting it? So the steam comes into the condenser and water comes into the condenser through the tube, okay, of the condenser, and then the steam is cooled and condensed. So the condensate is sent to the condensate line. There's usually a condensate pump that will take the water from the hot well into the condensate line back to your deaerator, okay. So the cooling water, having gained heat from this heat exchanger, is discharged through this line. Are we getting it? Back to your cooling tower, okay. So this is the condensate line. Like we said before, the condensers, they are basically heat exchangers, shell and tube heat exchangers, and that is what you are seeing here now, okay. So these are the tubes of the heat exchanger. This is a 4-pass tube heat exchanger, okay. So this is what you are seeing here now. So the steam is administered into the condenser from here, and then the condensate is taken out from here, okay. So while cooling water goes into this tube, are we getting it? To cool that steam, to help condense the steam. So in the condensate system, we have a system that helps to pull vacuum, okay, and that vacuum system helps to increase the efficiency of the entire unit. So this vacuum system, okay, as it's pulling the vacuum, what happens is that those non-condensable gases that are around, remember, as the steam goes put into the condenser, okay, the steam is cooled and then it is condensed into water. Then as that is happening, you see that reduction in pressure, sharp reduction in pressure from as you condense from steam to water, that reduces the volume, okay. That reduction in volume causes change in pressure, okay, causes reduction in pressure. So that reduction in pressure is what will help to create that vacuum. Are you getting it? That will now pull more steam into the condenser, this unit. But the thing is that the possibility of us having non-condensable gases within the system, especially if even if your deaerator is very effective. The possibility of having non-condensable gases, okay, within the steam will be there. That may be as a result of leakage or poor water treatment, or ineffective water treatment. But the non-condensable gases must be there. So those non-condensable gases, if you don't remove them, okay, it will distort the vacuum. That is, it will break the vacuum of the condenser. And once the vacuum is broken, you see that that will affect the efficiency, because it will cause the steam not to be flowing to the condenser at the rate at which it's supposed to flow. Okay, so to help us to remove those condensables and help us to non-condensables, I mean to say, and help us to create that vacuum, especially during startup of the steam turbine, you see that we have a vacuum system. Okay, so this vacuum system, you see that it is connected to the part that is connected to the exhaust of your steam turbine. So this part which is connected to the exhaust of your steam turbine, this is the hot well. Okay, this part that is connected to the exhaust of your steam turbine is where this is connected to. Are you getting it? That is, it is connected to. Okay, we'll see that clearly later. Okay, which is this part that is connected to the exhaust of your steam turbine. Okay, that is the part where it is connected to. So now, if you look at, let's take a closer look of this vacuum system. Okay, and see how it works. Okay, so this is a closer look of the vacuum system. So this is connected to the exhaust of your steam turbine. So those non-condensables will definitely be present. Okay, the water have been condensed and they will fall into this hot well. So your condensate will be extracted from this hot well. So those non-condensables that are here, this vacuum system will help us to remove them. So we have these two ejectors here. Okay, so the steam is actually administered. The steam line is connected to this part of it. Okay, so as you open this valve, okay, you see that that steam will now flow through this ejector. So as it's flowing through this ejector, you'll see that it will now create a kind of lower pressure because it is throttled here. Okay, create lower pressure here. That lower pressure will help to draw whatever that is contained here. Are you getting it? So everything here will be pulled through this and then to this heat exchanger, which is also a condenser again. Are we getting it? So everything is pulled through. So as the ejector is working, it is pulling those non-condensables from the condenser itself or the exhaust system of the steam turbine. So thereby creating vacuum that will be needed within the condenser. So those non-condensable, along with some steam, especially during operations, will be sent to this cooler or heat exchanger. So here it is cooled further, okay, and then as it is cooled, the condensate will be sent back to the condensate line, while the non-condensable will be ejected to the atmosphere. Are we getting it? In some system, we may have another ejector system that will assist us, okay, in pulling those non-condensable from the condenser and then the with air-peace steam anyway. So those non-condensable and the air-peace steam will be discharged into the atmosphere. That is how vacuum is pulled within the condensate system. So the condensate now will be recirculated by the condensate pump. We'll see that later. The condensate pump will now send it back to your deaerator for further use. Okay? After deaeration, it will be sent to the boiler once again to generate more steam. So it actually helps to increase the efficiency of the entire system. So you see that since the condensate will be sent back to the deaerator and back to your boiler, there won't be any need to treat more water. Okay, so it's just the makeup water that you need to treat. Are we getting it? And add to your system. So here we have an example of a vacuum system that helps to pull vacuum. So this here, this is attached to the exhaust system of the steam turbine. Okay, so you see that, and it's connected to these two ejector system. Okay, so you see the two ejectors. So once steam is administered into this ejector system, what happens? You see that as it's working, it pulls vacuum, okay, or pulls whatever that is on the line to your exhaust system, okay, through into this condenser again, which is a heat exchanger. Are we getting it? So so in this case now, you see that these condensers, this line, you see that it is connected. This is the steam line. So you open the valve on this line, okay? Open this valve that will administer steam. So as the steam is ejected through this ejector, okay, it is throttled here, then that will a kind of create low pressure around this area, which will help to pull whatever that is on this line connected to the exhaust system of your steam turbine, pull all to through the ejector, okay, into this heat exchanger, which is a condenser again. Okay, so the condensate here is returned to the condensate line, while the non-condensables, they are exhausted into the atmosphere by this line. Okay, so that's how it actually functions. So this is the ejector, okay, as we have discussed earlier. So we have the valve. So this is connected to the exhaust system. Okay. So in this case, we have a primary and secondary ejector, which means we have two sets of ejectors in this system. Are you getting it? So this is what we are seeing here. Okay. So this is the secondary ejector. So this is the secondary ejector. The one that we discussed earlier is the primary ejector. Okay. So you see that line, this so you see that condensate line is connected to this exhaust system down close to the condenser. This is the exhaust system. So all the vacuum is pulled, all the non-condensable they are pulled from. So here we have the steam turbine. Okay, so this is the exhaust and this is the intake to the steam turbine. Okay. So you see this is the intake to the steam turbine. Okay, so you see the this is where it is connected to the exhaust system before it comes to the condenser. Are you seeing it? So here is where is what here is the connection from the ejector system, which is the vacuum system. So once those ejectors are working, it pulls vacuum through this. Okay, so all the non-condensable within the exhaust system to the condensers, they are all pulled through this. Are you getting it? To the ejector and then discharged to the atmosphere. Okay, so all that we have been discussing since, this is an example of it. Okay, the exhaust to your condenser. So the vacuum is pulled from here. So this is the intake, huh? And this is the exhaust to your condensers. So here we have the cooling water system, okay, that helps to circulate cooling water. So this is actually meant, this system or this steam turbine is actually meant to drive a generator, as you can see on the screen. Okay, so putting all together, the, the operational cycle of the steam turbine. Okay, remember we said it starts from the boiler house. So in the boiler house, you see that the heat energy that is contained, the chemical energy that is contained in fuel is converted into heat energy by burning it. So as you burn that fuel, heat energy is generated, and that heat energy will now be absorbed in by the water in the tubes, okay, of that boiler. So you see that as the water is going into the boiler, it absorbs the heat and then it comes to the steam drum. So those water that have enough energy to that have been evaporated, have enough energy to go into the vapor phase, will be freed, okay, will come out as steam. And that steam is what will now be sent into your steam turbine. Okay, so we have seen the generation of the steam, then the admission of steam into the steam turbine. Okay, then here you see that the nozzle throttles that steam, and then as it impinges on the rotor, it is now converted into rotating mechanical energy by the turbine instead. That is the rotor, okay, of that is the rotating blade of on the rotors, okay. So as the steam is moving out, more energy is absorbed from it until it comes to the exhaust. This is the exhaust system. So in the exhaust system, we have, this is a condensing turbine now. Then we have system that helps us to pull vacuum on this exhaust system to establish vacuum. But ordinarily, without that vacuum system, you see that this condenser, its work, it sends in cooling water, okay, and that cooling water will help to condense or cool the steam. And as it is condensing, what happens to the volume? The volume will shrink. So by virtue of the fact that the volume is shrinking, that will create low pressure, okay, upstream of the flow of the exhaust. Are you getting it? So that low pressure that is created here will make more steam to be flowing through to the condenser. That will invariably increase the efficiency of the turbine. Okay? Then remember we said here we may have non-condensable gases after the condensation of the steam to water. Okay? This is the hot well now of the steam turbine. So those non-condensable gases, if we allow them to continue being here, it will increase the pressure in the exhaust section, thereby reducing the efficiency, okay, preventing more steam from flowing through. So those non-condensable, we need to remove them, and that is what we did with that vacuum system on the condenser. So that vacuum system will help to pull vacuum here, okay, thereby pulling the non-condensables out of this condenser, okay, on the exhaust line. Are you getting it? So as that is happening, we said some of the steam will be pulled along with it. Good enough, it has done its work. So we condense it there, okay, and send it back to the condensate line. So this condensed steam or condensate will now be sent back, okay, to your deaerator, though, but for simplicity, the deaerator is not here. So your deaerator, before it will now be sent to your boiler again, the cycle continues. Okay. Then remember, the function of the uh, steam turbine is to convert the kinetic energy that is contained in the steam into rotating mechanical energy that will be available on this shaft. So that energy will now be transferred to through the shaft of this generator, okay, and then will now be converted from that rotating mechanical energy by the generator to electrical energy. So this is for electricity generation. So this rotating mechanical energy can also be used to drive pump, drive fans, drive compressors. Are we getting it? So that is what the steam turbine actually does, and this is all you actually need to know about the steam turbine. Okay.